And indeed, I got other prizes, but I think the Shaw Prize is the most prestigious prize that I got so far.
Yeah. Okay, yeah, and, fingers crossed for more.
Okay, and actually it was quite surprising that they don't tell you anything. So I had no idea before.
Okay. Yeah.
And you know, I kind of, apparently they sent an email message a few hours before they announced it, but I didn't read email. And I just went from home to the university. At the time I was in Israel, although I'm in Princeton, but still I spent some time in Israel. And I was just about to go to the office in Tel Aviv. And then I see a WhatsApp from some friend mathematician who tells me something, congratulations, and I had no idea what he's talking about completely. And I said, thank you. And then when I came to the office, I saw this email, which really looks at the beginning like something phony. So I was not completely sure, but then I looked at the recording. So they really don't tell you before, and it came as really a surprise, a very nice surprise.
Okay, no, that's brilliant. I guess then, given you weren't able to travel to Hong Kong last year, then you're obviously, I guess, excited to be here now.
Yeah. So this was, I mean, they had some nice online ceremony, but of course, coming is a different experience, which is very nice. Yeah. So they did it now for several years that were only online during the COVID time. So this ceremony was for 4 years together, actually.
Oh wow! Okay.
Yeah.
So you actually were presented the prize sort of in person yesterday, or
yeah.
Oh wow!
Right. Yeah.
Oh wow! Well, I feel honoured to be speaking to you so soon after the official.
Okay. Yeah.
That's very cool. All right, fantastic. And having looked through your sort of, I guess, online biography and career and everything, many things stood out, but in particular, the amount of work that you've been able to produce over your career, to me, just seems incredible. I think I saw somewhere was quoting 500 publications. Somewhere else told me 600. Do you know the number?
I have an estimate for the number, but I think really is the number of publications is not so crucial, right? So that just says how people work. You know, some great mathematicians in the past. So Euler wrote many hundreds of papers, but and maybe there are equally famous mathematicians who wrote much less. But this just says something about the way you work. What is important is the quality of your best things, and not the quantity. But I like to talk with lots of other people, and maybe to collaborate with many people, and as a result, maybe I publish a lot.
No, I think that's a good thing, this idea of collaboration. And again, something else that struck me looking at the range of work that you've done was it really does cover mathematics and computer science.
Right, yeah. So I like to, in general, I think one of the nicest things about mathematics is to find maybe sometimes unexpected connections between different areas, and so I like to do that when I can, and I also like to work with people from other areas. So definitely computer science, but even sometimes people in computational biology, in economics, even, or neuroscience. So this happens, and the thing is that mathematics is really used in all kinds of in all scientific areas. So and discrete mathematics in particular, maybe because it's all basics, and then this the techniques there are relevant to other areas, and I like it when I can discuss problems with other people.
Do you, just because we've been talking about the vast range of publications, have you therefore had work published in biology journals, economics journals?
Yeah,
like
some.
Whole, I do, but that's quite fascinating to see a sort of theoretical or pure mathematician such as yourself being able to, well, let's say a subject that maybe would be seen by many people as traditionally on the pure side, but yet have this kind of wide range of applications. Just to me, it's just very interesting.
So, but being a mathematician yourself, you know that mathematics is relevant to pretty much everything. Yep. So maybe it's not so surprising, right? So
not surprising to us, potentially surprising to others.
Maybe, but the experience is interesting. So I have one paper in Science, so this is together with some people in biology. So it was really a question that was related to something I've been working on in computer science and combinatorics, but it was relevant to some problem in biology, and the experience also was interesting because working with people from that discipline and also publishing in that journal is very different from the things I'm used to in mathematics. So just to give you one idea, apparently whenever you publish a paper in Science, they tell you just before after it is accepted, but just before it appears, they ask you not to hold any press conference and report about the result before it is being published. And, so as mathematicians, we don't hold press conferences before, but really my tendency was to tell them that I'm sorry, I always hold press conference before any result is published. And but I resisted this temptation. And,
Do you prefer degrees or radians for measuring angles?
Degrees, I think. I would say degrees usually.
Okay.
But,
surprising. I would have gone radians but that's interesting.
If I write, okay.
No.
I don't.
Sorry, I said I wouldn't question. I apologize.
Right.
Okay. Whiteboards or blackboards?
It's also maybe I'll say blackboards, but I'm okay with whiteboards also. Okay. But blackboards, in Princeton we usually use blackboards, right?
Yeah, I had a blackboard installed in my office.
Okay.
Get rid of the whiteboard.
It is,
I was discussing before about all of these different range of subjects that you kind of covered with your research. So how do you decide what you actually want to work on?
Right. So I think I just if a problem looks interesting to me, then usually I'll think about it, and it's so of course there are problems that I know that have a long history and have been open problems for many years, and then I know that maybe I'll think about them more seriously, but usually, if something looks to me interesting, then I'll think about it, and it's and I think at least my experience was that you develop a taste over the years, and it's better to think about the things that you like than to try to think too much about what is important, what may have applications, and what. And in several cases, it happened to me that something that I thought about that looked maybe somewhat artificial turned out to be kind of important or had other applications. Sometimes also not, but this is right.
And when you say you think about it, I can imagine you're if you were to think about everything, then your brain would just be
sure, right.
So how do you know? So you've presented with a new problem. You've thought about it a little bit because it piqued your interest, your curiosity.
Right. Yeah.
But then how do you know if it's worth pursuing?
Yeah.
I guess because I think anyone perhaps who is an academic mathematician is very likely to hear interesting things all the time, and I think something that a lot of sort of graduate students, let's say, struggle with is deciding which things are worth my time in pursuing.
Yeah.
And which things are just, I have too many things going on, I need to ignore this. So when you think about it, how do you then know, I should continue with this? Is it whether or not you have a good idea in that short time frame, or?
Yes, so if it's indeed a new problem that I haven't heard before, then and it's interesting for me, then I try to think about it a little bit, maybe, and if I have any idea that looks relevant, or if it reminds me something that I've seen before, or if I think that something else may be relevant, then maybe I'll think about it more. And also, what often happens is that you hear some new technique, or maybe a lecture by someone else, and then it reminds you that this was something that you thought about half a year ago, and maybe it's relevant, and sometimes it's. But of course, it's important to realize that most of the time we fail. I mean, and this is true for all mathematicians, because otherwise you are doing too easy things. So most of the times you think about problems and you don't manage to solve them, but luckily, a mathematician is judged by the successes, not by the failures. So if among Riemann hypothesis, Goldbach conjecture, and the PNP problem, I'll only solve one of them, it will still be okay, right?
I think you will be more than okay if you solve one of those.
Yeah. So you don't.
Pi or tau?
Pi, maybe.
Okay. I don't know if you've ever thought about any of these questions before. Probably not.
Okay.
And then, do you have a favorite number?
Not.
It is valid not to have a favorite number.
I don't know. Not something I thought about, but.
I think most people assume that as mathematicians we have favorite numbers.
So. And those numbers are usually integers, or not necessarily.
It really depends. So mine is E is a good one. That's the number I pick. My favorite number is 3 divided by 2 to the power of 9/4, because it's a coefficient that appeared in my PhD thesis for a scaling argument. So it just popped out, and I was like, that's now my favorite number.
Yeah, so maybe I would, maybe for a favorite function, I would say log star or something, but favorite number, I'm not sure that I have,
All right.
Yeah.
For many people watching who perhaps are not necessarily academic or research mathematicians themselves, they might know your work from your number file video from a few years ago, which we were briefly talking about earlier, so it's always great to be sat here with a fellow number file presenter. So could you tell us a little bit more about that? And of course, I will link, for everyone watching, I will link in the description, so you can just go and watch the full video where we get the full explanation. But it was the necklace splitting problem, is that correct?
Yeah, so it was an interesting experience for me. I mean, I knew about number file before, but and maybe I've seen a few other pieces, but and I tried to explain something that I call the necklace theorem, that if I just say a few words about it, it's one way to describe it is that we have this necklace that has been, say, stolen together by a group of thieves. And let's say that we have 3 of them. I'll be specific with numbers, and luckily for them, so the necklace has beads of different types, and the number of beads of each type is divisible by 3, let's say.
Yep.
And then they want to split the necklace fairly among themselves so that each of them will get exactly the same number of beads of each type.
Yep.
So it's a fair splitting of an object, which is a problem that in mathematics has been considered before. It's a natural problem. And what I managed to prove some years ago is that for any necklace that has beads of, say, T types, if you want to split it equally among K, let's say 3 thieves, then it's always, you can always do it by cutting it in at most 2 times T places between beads, and then splitting the resulting intervals into partitioning them into 3 collections, and each collection will contain exactly 1/3 of the beads of each type. And this is tight. So there are examples showing that sometimes you need 2 times T parts. And what I like about the proof of this result is that it uses, so it combines combinatorial arguments with some argument for topology. So it really uses tools from a completely different area that maybe looks somewhat unexpected. And one interesting thing, by the way, is that because you use these topological ideas, then actually the proofs do not provide any efficient algorithm for doing it. Namely, these 3 thieves would know that they can do it in 2 T cuts, but they will not know how to do it. They can try to check all possibilities, but they cannot do it efficiently. So this was indeed some results that I liked, and I try to explain more about it in this number file.
And with you saying there that it doesn't give them a prescriptive algorithm to do this, does such a thing now exist, or can it never exist?
You mean about the
instructions
algorithm?
About how to do it?
Right, yes. So there are actually some indications that there is no efficient algorithm to do it because in complexity theory, we don't really know how to prove that things are hard, but we show that if they are easy, then some other problem we don't know to solve is also easy, and this is the situation here. So there are reasons to think that maybe there is no efficient way to do it. You can always try all possibilities because it's but this is not efficient.
It reminds me of the traveling salesman.
That's right,
Would it fall into the same category of problems, or is it slightly...
So these are more like search problems, because you see here, we know that a solution exists, but we don't know how to find it efficiently. And in the traveling salesman, it's more like asking, is there a tour of total length at most something?
And we don't know the solution actually.
That's right. But still, it's more or less the same, the same kind of things, right?
Fascinating. And the way you sort of describe that problem, it feels like a puzzle to me. And I noticed in your sort of online acceptance speech of the Shaw Prize in 2022, you mentioned that your interest in maths was sparked as a young child through puzzles.
Right, So I think that one thing I like in mathematics, and this is not uniform, I mean, some people may have different views, but I really like it when the problems that you are thinking about are very easy to formulate, so everybody can understand the problem, and maybe they are very hard to solve. Maybe some of them are even open, we don't know to solve them, but to just state what the problem is very simple. So it looks simple, but maybe it requires deep tools to be solved. But of course, there are some other mathematicians and that are doing much more abstract things, and they may have different views. But for me, like, the best things are problems that I can explain to a man in the street. Yes. The problem, maybe not the solution, but at least the problem.
Absolutely.
Right. Yeah.
And they tend to be the ones, just as you're saying this, I'm thinking of all of the famous unsolved problems, and I feel like the ones that capture people's imagination and become these kind of, they're almost like put on a pedestal of unsolved problems are exactly the ones you're describing.
Yeah, many of them, because in number theory, for example, right, because everybody understands what are natural numbers and what are primes, maybe, and so in some areas the problems are easier to formulate than in some other areas.
And just going back to the puzzles idea. Okay. So do you remember one of the first puzzles that you came across or that you were working on when you were younger that really, stuck in your memory as like, you loved it, it was particularly, as you say, probably easy to state and required quite a complex solution? Do you have any kind of memories of very early puzzles you did as a mathematician, or even when you were at school, that you can share with us?
Sure, I can think about some, but let me. So one example that I have is even more elementary than a puzzle. So this was when I was really a child. So maybe I was 11 or 12 years old, and still maybe it's an interesting story because this was something that kind of convinced me that mathematics is objective, and it's so let me try to tell it. So this was, I was, as I said, maybe 11 or 12. I was already interested in mathematics, but I didn't know much. And my parents had friends. There was this Eurovision contest. So it's a song contest in Europe. Yeah. And they were trying to kind of amuse themselves by trying to guess what would be the results, the end results. So every person who was there gave his or her guess for the end ranking, which country will be first, which will be second, and so on. And then once the final results were announced, then they gave a score for each one to see how good his or her guess was. And this was, if I'm using technical terms, the L1 distance between the ranking of the person and the actual ranking, which means that if someone guessed that some country would be first and actually it was fourth, then we take the difference between these 4 minus 1, and then we sum it over all the countries, and this is the score. And the smaller it is, then the better the guess was, because if so then they had everybody had his guess, and then the results were announced, and they computed the scores, and it turned out that all of them were even integers. Okay. All of them were divisible by 2, and then they started. So nobody there was a mathematician. They started to discuss it, and my mother, her background is in history, but she had a good mathematics intuition, and she said that she's sure that this should always be an even integer. And there was some guy there who was actually an engineer, and he said that it's not true, he doesn't believe it. And so my mother said, let's ask Noga. So indeed, I was maybe only 11, but she knew that and maybe I'll be able to tell them. And she called me, and they told me the problem. And indeed, I thought about it, and it's not so difficult to prove that it is always even. The answer is always even. But what was nice, so there was this engineer, and at the beginning he insisted that it's not the case, and then I kind of explained the proof, and after some 10 minutes or something, I was able to convince him, and he said, you know what, you are right, I was wrong, and this was what convinced me. You see, this is something that is special about mathematics, showing how mathematics is objective. there was, I guess, never a case where two people are arguing about, say, a political question, and at the end, one of them will say to the other one, "You are right, I was wrong." Yeah. No, I mean, everybody, but in mathematics, even a child can convince some grown-up who is an engineer, and the guy would admit at the end that I was wrong, you are right. Yeah. So the fact that these things that are true stay true and are true forever, this objective nature of mathematics was something that really appealed to me. And, I think, so of course this is not a serious mathematical puzzle, but still, I think it's an interesting story, and
absolutely,
and and it captures something about the objective nature of the subject.
I think the fact that you were able to work that out at the age of 11 or 12 I think shows a lot about your passion for mathematics at an early age, actually.
Yeah,
as
well. So it's not very difficult, but sure, I was I always liked these puzzles, right? Yeah.
And final question, more from me: would you describe yourself as a mathematician or a computer scientist, or neither, or both?
Yeah, I'll probably still describe myself as a mathematician, but one who likes to apply mathematical methods also to computer science. But both would also not be such a bad answer, right? Yeah. Yeah,
it sounds like you do everything.
I'm not very decisive. No, I mean, economics and biology, I'm not doing really seriously. So this is if the questions come. But computer science and discrete mathematics, I do seriously. Right?
Brilliant. Well, thank you so much.
Okay, thank you.
It's been a pleasure, and thank you to all of you for watching. If you have enjoyed this, at least half as much as I have being able to talk to Noga, then do please subscribe to the channel. It really helps. And I will see you all very soon with some more maths.